Hello and welcome to this Chemistry World webinar, Advances in Reaction Monitoring with FlowNMR. I'm Natalie Starkey, Chemistry World's science media producer, and I'm here with you for the next hour where we'll be hearing from two scientists from Oxford Instruments about how the benchtop X-Pulse and FlowNMR are revolutionising reaction monitoring. I'd just like to point out that this webinar is recorded, so if you find that you missed anything today or just want to watch again, then do look out in your inboxes for a link to the recording in the next few days. Now, here at Chemistry World, we're very happy to be working together with Oxford Instruments, who are a leading provider of high technology products and services to the world's leading industrial companies and scientific research communities. They exploit their world-class ability to image, analyse and manipulate materials down to the atomic and molecular level. The organisation's core purpose is to support the scientific community in addressing some of the world's most pressing challenges, enabling a greener economy, increased connectivity, improved health and increased scientific understanding. Now today we have Asad Saeed and Robin Blagg joining us to speak more about magnetic resonance benchtop NMR spectroscopy. I'm actually going to ask them both to turn on their cameras now. We've got Robin on screen already, just so you can see the both of them. They'll be sharing the presentation today, and then at the end of the webinar, we're going to have some time for some Q&A, and I'll explain in a minute how you can send in your questions for them both. But a little bit about our speakers first. Asad Saeed joined Oxford Instruments Magnetic Resonance in October 2023 as an application scientist for the X-Pulse broadband benchtop NMR spectrometer. Asad completed his first degree at the University of Kent, carrying out a master's project in organometallic chemistry. Asad has almost finished writing up his PhD in FlowNMR at the University of Bath. And we also have Robin Blagg, who joined Oxford Instruments Magnetic Resonance in October 2020 as the lead application scientist for the X-Pulse, subsequently being promoted to applications team leader. Robin completed his first degree at the University of York, then obtained his PhD also in organometallic chemistry at the University of Bristol, and undertook postdoctoral research at the Universities of Sussex, Manchester and East Anglia. Robin is a chartered chemist, member of the Royal Society of Chemistry, and serves on the committee of the RSC NMR discussion group. So we're really looking forward to hearing from these two very experienced speakers today. Now, I don't want to take up too much more of your time before handing over to Robin and Asad, but I wanted to let you know that as with all Chemistry World webinars, this session is interactive, which means you can ask questions about any aspect of what's covered in today's event. So please use the questions box to send in your questions as soon as they come to mind, even during the presentation, and I'll be able to put those to our panel in the live Q&A towards the end of the webinar. Now, you won't normally be able to see other people's questions in the questions box, but don't worry because myself and the Chemistry World webinars team can, so do start sending them in soon. So without further ado, let's hand over to our speakers to begin. I think we're going to start with Robin. Brilliant, I'll leave it to you.
Thank you, and welcome everyone, and thank you Natalie for the kind introduction. Today I'm going to give a quick introduction to NMR for those of you who aren't already familiar with it, and a quick refresher for those of you who are. Then Asad's going to introduce FlowNMR as a technique and discuss a range of applications of FlowNMR. Finally, I'm going to present the instrument that we use to acquire all the data in this webinar, the X-Pulse broadband benchtop NMR spectrometer, before summarising the whole presentation and giving an opportunity for questions at the end, as Natalie's already mentioned. So let's get started with a brief introduction to NMR spectroscopy. While I expect many of you are already familiar with NMR, for those who aren't, I'll briefly walk through a simplified version of the fundamental process to provide a general understanding. We start with the concept that all nuclei exhibit a fundamental property known as spin. The vast majority of nuclei have a non-zero spin, giving rise to a magnetic moment for each nucleus. This is where we get nuclear from. A bulk sample contains many nuclei, and the spins are randomly orientated. When we apply an external magnetic field, there is a preferred orientation for the spins to align. And with the majority of spins aligned with the magnetic field, a net magnetic moment results. This is where our magnetic comes from. Once we have spins aligned with the magnetic field, we can start to manipulate them to provide useful information. To do this, we can use one or more radio frequency pulses. The pulses rotate the net magnetic moment of the sample, making it resonate, giving us the resonance of NMR. This rotation of the magnetic moment induces an electrical current in the detection circuit that can be measured as the sample relaxes back to the equilibrium state. This gives us the basic NMR signal of free induction decay, or FID. Repeating this loop generates more signal by combining multiple FIDs. Finally, you apply a Fourier transformation to the FID, generating the typical NMR spectrum, which might look something like this. While I'm not going to describe how to interpret an NMR spectrum in any detail, there's a few points it's important to emphasize here. Each chemically unique environment in the sample gives rise to a different signal in an NMR spectrum. These signals appear at different frequencies, or chemical shifts in NMR, and comprise one or more individual peaks. The total integrated area of a signal corresponds to the number of nuclei which gives rise to that signal. In the case of a pure small organic molecule like we're looking at here, consideration of all these factors allows each signal to be assigned to an individual hydrogen environment in a molecule, which can be used to identify the molecule in the case of an unknown. Of course, we're often not looking at a sample of a single pure compound. In this spectrum, we're looking at a mixture of 4 phosphorus-containing compounds. Since each compound contains a single chemically unique phosphorus environment, they each give rise to a single signal in the phosphorus 31 NMR spectrum. Each signal can be assigned to a different compound and then integrated to accurately determine the amount of each compound present in the system. Therefore, in spectra comprising multiple signals from multiple species, it's possible to both identify and quantify the species in a mixture, as shown here for a mixture of ibuprofen and paracetamol. But how do we actually acquire these spectra in practice? Most people who are familiar with NMR spectroscopy will think of something like this, and I've just realized the animation's done the wrong way around. Think of something like you're looking at on the left. A high-field instrument built around a large superconducting magnet filled with liquid cryogens and with a separate console containing the signal generator, radio frequency transmitter and receiver, and the other electronics required to acquire NMR spectra. Benchtop NMR, as shown on the right, replaces the large superconducting magnet with a permanent magnet, significantly reducing the size of the system, thereby greatly increasing its flexibility. In this case, the X-Pulse magnet and console are on a mobile workstation, together with a PC to control the instrument, and a UPS to keep it powered while it's moved. This makes benchtop NMR much more useful for applications like FlowNMR, which Assad is now going to introduce.
Right, thanks, Robin. Hi, everyone. So I'll first give you a little introduction on what FlowNMR is. I'll speak about how it works. I'll briefly discuss its development over the years. I'll then go through some key features of FlowNMR. I'll touch upon some of its applications before delving into how we can leverage our 60 megahertz broadband benchtop system, the X-Pulse, to perform reaction monitoring by flow. Finally, I'll showcase several practical examples demonstrating the utility of FlowNMR before handing you back over to Robin. Right, so what is FlowNMR? So FlowNMR refers to the real-time non-invasive monitoring of dynamic changes with a flowing system using NMR. A basic FlowNMR setup consists of a magnet, in this case it's our 60 megahertz broadband benchtop system, which is interfaced via a flow system with an application. Typically, the application can be a reaction occurring in a Schrank flask, as seen here, a pressure reactor, or even a biological specimen. It doesn't really matter, as long as you can accommodate the necessary tubing connections and the sample mixture is homogeneous. So most often, this technique employs a closed loop flow system in which the bulk reaction mixture is circulated through the detection region using a positive displacement pump. In this case, it's just a standard peristaltic pump, which is then circulated back to the original reaction vessel. So essentially, by maintaining a continuous flow of the sample through the detection region in the magnet, FlowNMR facilitates high-density data acquisition under realistic conditions, providing rich, quantitative information into a wide array of solution phase systems. So from chemical reactions to exploring various fluid dynamics. So FlowNMR has an interesting history, stretching back over 7 decades now. So the technique was first explored by Suryan in 1950, who investigated the effects of flow rate, T1, T2 relaxation times, and signal intensity in a flowing sample of water and ferric chloride through an NMR probe. So early FlowNMR setups required custom NMR probes, and as you can imagine, limited its widespread use. By the 1970s, the integration of liquid chromatography with NMR, also known as LC-NMR, broadened the possibilities of structural elucidation of isolated organic compounds, significantly enhancing the technique's utility. The field went relatively quiet until the early 2000s, with technological advancements such as 3D static mixers for effective homogeneous mixing and the emergence of compact, low-cost NMR instruments. However, it was not until the design of the online NMR umbilical in the early 2010s by Foley and co-workers that allowed for easier integration with existing high-field NMR setups. But most recently, the advancements of benchtop NMR systems has enabled the adaptation of FlowNMR for reaction monitoring at low field. This implementation of magnet configuration and the flow cells within these systems has dramatically improved the precision and utility of low field monitoring. Right, so as mentioned, FlowNMR operates under realistic conditions. So what do I mean by that? Well, the technique is scalable and can accurately represent large batch processes you might find in actual industrial or laboratory settings. The user has full control over various parameters, whether it be temperature, pressure, or carry out reactions without the inclusion of air, moisture, and light for more sensitive analyses. FlowNMR allows for the addition of reagents at any point into the system. This provides flexibility and the ability to react to changing reaction dynamics in real time. But most importantly, it ensures proper mixing, which of course avoids mass transfer limitation. This aspect makes FlowNMR particularly advantageous for operando monitoring, where small changes in process conditions can significantly impact catalytic speciation and reactivity. So for those interested in understanding how different types of NMR monitoring can influence kinetic analysis, I highly recommend reading this 2016 study by Foley et al. Right, so efficiently implementing FlowNMR, whether at high field or low field, can present several challenges that can affect the outcome and effectiveness of monitoring reactions. These challenges stem primarily from 2 areas: acquisition considerations and engineering considerations. So I won't go into much detail today. This area could easily fill an entire webinar on its own. But these variables listed here should be generally considered to account for common pitfalls when acquiring and quantifying FlowNMR data. But there are 2 common practices I see, which I believe people should avoid if possible. The first is acquiring FlowNMR data, but not accounting for the different flow effects that are generated from a flowing sample. Essentially, due to the partial magnetization of a flowing sample, this can lead to a reduced signal intensity when attempting to quantify your chosen reaction species. A correction factor should therefore be applied to each peak of interest to account for this to ensure quantification. The second example is having to perform a stop flow type monitoring where the sample is stopped for detection to ensure quantification, which can often lead to longer times for spectral acquisition and for samples to not be representative of the bulk, which is particularly troublesome for faster reactions. So from an engineering perspective, it's essential to ensure that the FlowNMR system is chemically compatible. So all materials in contact with the reaction mixture must resist corrosion or reaction. Likewise, are able to provide controlled reactions conditions, so maintain consistent temperature as mentioned, pressure and atmospheric conditions throughout the flow path, and capable of delivering a smooth, controlled sample flow. This risks essentially blockages and maintains steady state of data acquisition. And lastly, the user must ensure that the system is safe for the routine operation, especially in a multi-user or unsupervised setting. So if you're interested to know more about the ins and outs of FlowNMR, then I would recommend this 2016 paper by Hall et al. And this collaborative paper in 2021 breaking down each hardware component, which makes FlowNMR easier to understand and implement, both at high field and low field. So having discussed the fundamentals of FlowNMR, let's explore the diverse impactful applications this technology enables. So FlowNMR is being increasingly utilized in a variety of sectors over the last few years, both at high field and low field, due to its ability to provide real-time insights into the dynamics of chemical reactions and other processes. So here are some key areas where FlowNMR can prove to be invaluable. In chemical reaction monitoring, so this includes high pressure reactions or photochemical reactions in battery technology, whether it is in the lithium ion extraction from brines or assessing electrolyte properties. As you can imagine, in research and academia, so providing essential data such as reaction kinetics for the development of kinetic models or understanding reaction mechanisms. It's been utilized in the pharmaceutical, drug, vitamin industry, and also now in polymerization reactions where it can be equipped with diffusion type experiments, which I'll mention later on, to monitor polymer growth. And of course, several other applications. All of these applications are all areas that the X-Pulse can be utilized to monitor these transformations. So I'll now focus on how we at Oxford Instruments can facilitate these applications through our 60 MHz broadband benchtop system, the X-Pulse, and how it enables efficient and effective FlowNMR for real-time monitoring across various sectors. So where are we at with FlowNMR monitoring using benchtop? Quite far, I'd say. If we look at the illustrative setup using a pump, the reaction mixture can flow directly from the reaction vessel through the flow cell in the X-Pulse and back into the reaction vessel for continuous monitoring. The X-Pulse benchtop system offers several advantages for FlowNMR reaction monitoring. So let's start off with the flexibility of placement. With a smaller footprint and a user-friendly setup, this system can be placed in various environments, allowing for continuity of analysis, whether you're working in a lab fume hood or the need to monitor larger reaction vessels during the process development, or even if a user would want to bring the instrument to the manufacturing site. The X-Pulse offers the portability and versatility to meet those needs without the need for a dedicated facility. So the X-Pulse essentially distinguishes itself with its user removable probe, allowing for fast installation of the straight-through 4 mm flow cell. This design enables setup changes in under 20 minutes, significantly reducing the downtime and enhancing throughput in dynamic research schedules. So this convenience is crucial when reaction monitoring needs to be efficient and adaptable to different setups. And once done, you can easily remove the flow kit if needs be and acquire in a normal tube within an hour. So that sounds quick, right? Well, we have excellent temperature control and our shimming capabilities, both static and in flow also ensure stability and precise lock-in. So ensuring a consistent sample conditions and reliable data across the experiments. This reduces the variability that is common among other benchtop systems. This means we do not need to shim once acquiring. This is particularly important when dealing with flow conditions, where maintaining consistent sample homogeneity is critical. With our external deuterium lock, the need for deuterated solvents is eliminated, allowing for greater flexibility in sample preparation and reducing costs. The X-Pulse also offers features like its 3-axis field gradients as standard, so allowing for enhanced gradient field homogeneity and efficiency, directly impacting the quality and reliability of our pulse sequences, which utilize shape pulses, for example, diffusion and selective excitation measurements. This capability can be especially useful in complex reaction monitoring scenarios where accurate data is essential. So, time for some real data. So in this section, we'll look at a couple of examples of proton FlowNMR monitoring performed using the X-Pulse. So first, we have a simple esterification reaction forming ethyl acetate and water from acetic acid and ethanol using an acid catalyst. We can clearly monitor the reaction progression over time. By examining the key peaks, we can identify when a product is forming or when the reactants are being consumed, as you can see in this conversion profile. So moving on to a slightly more complicated example, where we can monitor the transformation of an aldehyde complex with an alcohol with a catalyst. We are able to clearly integrate the various species and obtain crude integral against time profiles. We are able to monitor substrate consumption, multiple product formation peaks, as well as intermediate species, as you can see here at 4.6 ppm. So generally, from this is the next important step. So through the proper processing, taking correction factors and accounting for the number of protons for each peak, you are able to accurately and quantitatively obtain these reaction profiles, where you can quantitatively observe the product being formed, substrate being consumed, and the intermediate peak appearing over time. So that was a couple of examples of proton NMR. So now, having looked at the basic proton monitoring, let's look at the X-Pulse's advanced 3-axis gradients enhances our FlowNMR capabilities, particularly when measuring diffusion. So in NMR, alignment of the Z-axis with a magnetic field, B0, is a standard. The X-Pulse's magnet design ensures that B0 is perpendicular to the sample. This configuration significantly enhances the gradient's field homogeneity and efficiency, which is crucial when we measure diffusion using FlowNMR. The X-Pulse features a 3-axis field gradients as standard, with the Z-axis reaching up to 0.5 Tesla per meter. This configuration directly impacts the quality and diffusion measurements by enhancing the signal-to-noise ratios and ensuring that the data is reliable and consistent. This is particularly valuable in environments where the Y-axis experiences significant disruptions due to the alignment with the magnetic field in other systems. Moreover, the X-Pulse is equipped, as mentioned, with specialized pulse field gradient spin echo experiments, so PGSE, that can cater to a broad range of nuclei. These experiments are pivotal in accurately measuring the diffusion constants, providing deeper insights into molecular sizes, shapes, and interactions. This setup also ensures that only the changes to the sample between the gradient pulses are due to diffusion, and of course allowing for precise calculations of the diffusion constants. So the diffusion constants are typically obtained through a linear Schedkow-Tanner plot, which requires a smooth variation in signal intensity with gradient strength. So here we have examples that show the measurement of diffusion of water in the X, Y, and Z axis under static conditions, and also showing the smooth curves for the signal and attenuation as the gradient strength increases. and the linear sketch-code Tanner plots on all three axes. Now, here we see the measurement of the diffusion of water on the X, Y, Z axis once again, but at a flow rate of 1 ml/min. These results clearly show that diffusion measurements along the X and the Z axis remain consistent, whereas as you can see with the Y axis experiences significant disruption, demonstrating the importance of this alignment. This distinction sets the X-pulse apart, where the Y axis is aligned with the magnetic field, so you don't need to worry about this. And once again, at an even increased flow rate of 8 ml/min, we can see that it gets worse. Right, so we are not limited to just 1D acquisition in flow. As shown with the PGSE experiments, we contain gradients which allow us to do shape pulses. This means we are able to acquire all of these sequences. All of these techniques can suffer similar issues as observed with the diffusion experiments if the gradients is applied in the same direction as a flowing sample. So when it comes to solvent suppression peaks that can easily obscure information, our solvent suppression techniques can reduce these dominating signals as shown here. Selective excitation techniques such as selective toxes and DPFG-SE NOSEs can enhance our ability to focus on specific molecular interactions, assisting here for accurate structure elucidation. We also use many more advanced programs extended to 2D like gradient selective COSEs and NOSEs, which can improve the resolution and clarity of complex mixtures. So the next example is in collaboration with the University of Warwick, where we look at polymer sizing by diffusion in flow using the X-Pulse. So as shown, DOSI can present unique challenges when applied in a FlowNMR setting. Here we share a FlowNMR experiment focusing on the polymerization of methyl acrylate using a raft agent. This study aimed to monitor the polymerization in real time to understand the kinetics and molecular weight evolution under controlled conditions. We acquired interleaved proton and PGSE experiments. From the proton data, we are able to obtain the change in concentration of methyl acrylate, as you can see here. We can also account for, you can clearly see where we've added more raft agent. You can see the change of rate, so this is quite clear. Likewise, when utilizing the PGSE technique, we are able to plot the relative gradient strength with the raw integrals. From this, we can take the natural log of the integral ratio, where we are able to obtain the sketch-code Tanner plot, and through the gradient of the line, we are able to obtain the diffusion constant. So now applying this process into every time point acquired, we are able to monitor the diffusion change over time, where we are able to clearly see how it changes. So polymers are not monodispersed. The diffusion experiments can provide an average diffusion constant and therefore an average molecular weight at each point. So from this, we can plot the DOSI molecular weight against time to obtain these informative profiles. So we've demonstrated 1D proton experiments and how we've utilized our gradients. The last set of experiments will be showing off our multi-nuclei NMR capabilities using FlowNMR. So the first example is in the lithium extraction from brines. The continuous monitoring of lithium and sodium by FlowNMR provides quantitative data and immediate feedback on the concentration changes of lithium and sodium ions in brine. This enables dynamic adjustments to the extraction process, operating within the optimal concentration ranges for maximum yield and efficiency. Unlike traditional sampling methods that may require stopping the process or removing samples from the system, FlowNMR performs analyses without disturbing the ongoing processes, which is beneficial for maintaining the integrity of the extraction process and preventing contamination. Operators can use the data to optimize parameters such as pH, temperature, and flow rates to improve lithium recovery rates and manage sodium and other impurities more effectively. So what does the data look like? Well, we can monitor the concentration changes of both lithium and sodium comfortably down to about 20 millimolar. we can clearly see where we've added in or when we've tried to make the sample more concentrated and less concentrated. We can track these changes over time, and likewise a gradual dosing to make the concentrations more dilute. So as mentioned earlier, there are several key considerations that are needed to ensure the generation of quantitative data. Here we have shown the inversion recovery profiles of both sodium and lithium, both at static and flow-in. So as lithium typically displays longer relaxation times compared to other commonly used nuclei, especially compared to sodium, quantification of the nuclei is particularly important here to ensure the measurement of precise concentrations. Too short of a relaxation time for sodium would result to not observing representable concentrations of lithium. Whereas too long would limit the time points that can be observed. This becomes particularly important when sharp changes in concentrations, as shown in the previous slide, can occur. To address this, it's essential to consider the relaxation delay, which should be ideally 5 to 7 times that of the T1 relaxation time, to achieve accurate quantification without compromising the frequency of observation. We can clearly observe the T1 reducing with increasing flow rate. So sodium typically exhibits rapid T1 relaxation times, enabling swift data acquisitions, whereas lithium is characterized by longer T1 times, posing a challenge for rapid analysis. Our investigations revealed a significant reduction in the effect of T1 relaxation time in flow from 22 seconds to 1.14 at 2 mils a minute, and taking this further to 0.63 seconds at 4 mil a minute, compared to the 22 seconds as mentioned under static conditions. So this is again because of something called outflow effects. I won't go into details, but essentially in a flow-in sample, your FID apparently decays faster as you measure a steady state of traveling premagnetized nuclei. Some of these leave the same amount, which is replenished with fresh premagnetized material. But because they are not the same, the apparent T1 reduces, which means that you can essentially pulse and acquire faster on a flow-in sample. So these measurements ultimately allowed for the optimization of delay times to approximately 0.5 seconds for sodium and 6 seconds for lithium at a flow rate of 2 mil a minute. So ensuring that we can acquire lithium, sodium, and proton interleaved every 8 minutes. So we can also perform phosphorus NMR reaction monitoring using the X-Pulse. So this is just a standard oxidation reaction of triphenylphosphine using hydrogen peroxide to form triphenylphosphine oxide and water. We can monitor the oxidation process and track the concentration change, as you can see here. So as the reaction reached equilibrium, we added some more H2O2, which allowed us to fully oxidize our triphenylphosphine to triphenylphosphine oxide between hours 10 to 12. And likewise, we are also able to effectively monitor the esterification of trifluoroethanol with acetic acid using an acid catalyst. We were able to perform interleaved fluorine and proton monitoring to form trifluoroethyl acetate and water, and we can intentionally see that as the reaction reaches equilibrium at 17 hours, you can follow the concentration change when more catalyst was added to the system at 18, 22, and 25 hours. So before I hand you back over to Robin, I welcome any questions at the end of the presentation, and also encourage anyone interested with using FlowNMR, or if you're not sure about quantification, to reach out to me, and I'm more than happy to discuss and advise. So we also are looking for and welcome any further collaborations, and the end goal is to, of course, build a thriving community where we can all work together for further progress in this fruitful field. And I'll hand you back over to Robin.
Thank you, Assad. Before we finish with the talk, we'll talk a little bit about the X-Pulse, the instrument that we use to acquire all the data that you've seen here today. The X-Pulse is, as Assad has already said, a 60 megahertz broadband benchtop NMR spectrometer with high resolution and sensitivity. Yet, with all the capabilities that you would normally expect to find on a high field instrument. including the 3-axis gradients we've already discussed, and shape pulses and gradients, which are required to implement many of the more modern advanced pulse sequences. In its broadband configuration, the X-Pulse has 3 channels: a proton-fluorine channel, the broadband X channel, which is capable of tuning to all NMR active nuclei with frequencies between 41 and 19% of the proton frequency, and a dedicated deuterium lock channel, which is usually used as an external deuterium lock. Hence, there is no need to have deuterated solvent in your sample in order to perform locked NMR experiments, something which is particularly important with flow applications where you wouldn't really want to be doing your synthetic scale reactions in deuterated solvent solely to benefit the NMR. In addition to the flow cell, the X-Pulse could be used with 25 position auto sampler or in a variable temperature configuration, allowing spectra to be acquired at temperatures between 0 and 65 degrees Celsius. The X-Pulse can be used to acquire the full range of 1 and 2-dimensional NMR spectra, which are commonly used for the characterization and analysis of small organic molecules. Quinine in the case of this example, and can observe on a single instrument at least one NMR active nuclei for all of the elements shown in on this periodic table in dark blue or dark orange. And the reason why they're shown in dark blue or dark orange simply indicates whether we've tried them before. So dark blue, if you email me about them, I could send you spectra today. Dark orange, we'd have to acquire them first. For example, the fluorine 19, boron 11, phosphorus 31, silicon 29, and platinum 195 spectra shown here. So finally, to summarize what we've discussed today, FlowNMR allows for the online monitoring of chemical reactions and processes, which is much more practical with a benchtop instrument than is the case on most high-field systems. The modular nature of the X-Pulse allows users to not only perform FlowNMR measurements on a wide range of nuclei, but also to switch to using standard 5mm NMR tubes, optionally with an autosampler, or to perform measurements over a wide variable temperature range, all on a single instrument. We thank you very much for your time and we'll be happy to answer any questions asked during this webinar. If we don't have time to answer everyone's question, we promise we will get back to you with an answer via email within the next week or so.
That's really lovely. Thank you so much, Robin and Assad. So much detail there. I'll just remind everybody as well that you will be sent a recording of this webinar within a few days. So if you missed anything, you need to go back and check, then it's all going to be there for you, so don't worry. And as Robin just said, hopefully you'll hear back if you have any questions, but you can contact Oxford Instruments yourself, and we've got the link there for the email address and also a link to their website if you need to check anything else out. So you've got those available to you. So we've got some questions coming in, which is brilliant. I'm going to start to get through some of them now. So do keep sending them in because we've got some time left in the webinar, so plenty of time to ask your questions still and hopefully get a live answer from Robin and Assad. Right, so let's start with actually a question that came in on email ahead of the webinar, which is always really nice to see. So it's Bernard, and he is from Zambia, so Republic of Zambia we're getting a message from, which is brilliant. So the question is, could you elaborate on the integration of FlowNMR with other analytical techniques or instrumentation platforms, and how this synergy enhances the scope and depth of reaction monitoring capabilities, particularly in complex chemical processes or multi-step syntheses? Quite a long question there. I'm not sure which one of you wants to take that, but I'll leave that for you to decide.
I can, that's okay. Yeah, I could probably spend a long time answering this question, but essentially, so we know that FlowNMR can't provide all the answers, but of course it can be used in tandem with various other analytical techniques such as, well, HPLC, UV-Vis, Raman, and mass spectrometry. And a benchtop NMR makes it much easier for that due to its practicality. And at the end of the day, you want to obtain a multi-dimensional view of your reaction dynamics, enabling detailed insights into the reaction intermediates, kinetics, or the product distribution. So by merging all of these nuggets of information that you can get from these different techniques, it can only advance the overall progress and the understanding for the information that you acquire. So honestly, there's absolutely no reason why you can't synergistically have everything together.
That's brilliant. I'm sure that's going to be good news. Yeah, really versatile. That's really, really useful. Let's move on to a question. Okay, so this one is, do you need deuterated, have I said that right, deuterated solvent in your reaction mixture when using flow?
Yes, firstly, yes, you did say that right. So as we said, is with the X-Pulse, you won't, because we would generally, so the reason we'd normally want deuterated solvents for NMR is because we'd be the twofold. You either want to run with a deuterium lock anyway in order to actually lock on your spectra, because as I showed initially, generally with NMR, we're acquiring multiple individual scans and adding them together to get the final signal. And in order to have a lock, we've got an internal reference to make sure all of those are perfectly aligned and stack up correctly. In that case, with the external deuterium lock, we don't need to do that. We can then have that without needing to add additional deuterated solvent to your sample. Now, of course, there might also be the reason why you certainly, when we're often doing analytical NMR in an NMR tube, is we're also working deuterated solvents, because then, at least in the proton NMR spectrum, we don't want to worry about large prominent signals from our solvent, which are likely to be a couple of orders of magnitude more intense. Now, there's a couple of answers to that. One of them is do NMR on a different nuclei that doesn't involve protons in the first place. So if we're doing the phosphorus or the fluorine that we were looking at today, or lithium or sodium, doesn't matter what the solvent is, be fully protonated. And pretty much in all those cases it was. Now, of course, if you look at something like proton, when you actually do have one or more solvent signals, this is when you take advantage of the capability to support more advanced pulse sequences by running what are called solvent suppression experiments, which allow you to actually run an NMR experiment that will intrinsically suppress one or more very prominent signals, so your solvent signals, and then allow you to actually more clearly resolve the remaining signals that are going to be your species of interest.
Okay, thank you. That was a great answer. Let's move on to, okay, can you acquire two-dimensional NMR spectra in flow? I'm not sure who wants to take that one.
Yes, well, in short, yes, we can. I think we've got a hidden slide for that. Do you want to?
Does someone want to share me?
Yeah, sorry everyone watching. We just got to, because they're Asad and Robin are actually sitting in the same room. You might not realise, so we just need to mute them each other out when they're speaking. So there's a little bit of confusion there, but I think we've got you now.
Sorry about that. Yeah, no, so the system is sufficiently stable enough to monitor 2D correlations. So this is a 2D correlation of ethyl acetate at 1 milliminute, acquired in 5.5 minutes or so. We can clearly distinguish the cross correlations between each peak, and that allows us, of course, to get additional information and increasing the flow rate to, do we have another slide? To 10 milliminute, again at 5.5 minutes of acquisition. I mean, 10 milliminutes is very much overkill. Standard practice, you would use between 3 to 4 mils a minute, but this is just to emphasize that even at these high flow rates, that you can still see the correlations and you can still get the data that you would want by 2D. And likewise,
Oh, sorry.
Yes, oh, sorry, no, but likewise. So we've just shown an example of a cozy spectrum there, but that stretches between multidimensional correlations, whether it's between your proton carbon HSQC or your proton phosphorus HMBC, for example. And then this is just to reiterate the point that at a higher flow rate, you can clearly see that signal intensity does reduce. So this is something that you need to compromise and bear in mind.
Okay, that's good to know. I think a question that's quite related. How long did each of the spectra take to acquire? How long are we talking for these?
So generally, with most of what we're looking at, we're probably reaction monitoring and flow, proton NMR, we're probably doing either 4 or 16 scan acquisitions. So generally 4 scan acquisition in flow with quantitative parameters, you're still going to do in more or less a minute. 16 scan, you might be looking for a little bit longer. Again, that works out about 4 minutes. As we said, the interleaved lithium sodium proton NMR that we did when we did the lithium and sodium quantification in flow, we were interleaving all 3 of those within individual 8-minute blocks. I think the fluorine NMR we were looking at, again, is probably 4 scan data, so it's going to be about a minute. And I think the actual PGSE experiments for the diffusion, for the polymer diffusion, so each PGSE run, I think, was 6 individual acquisitions with different gradient strengths. So they'd have been maybe coming out at about 7 or 8 minutes total, plus another couple of minutes on top of that for the standard one-dimensional acquisition we'd have acquired at the same time. So we were generally getting effectively another data point on that run every 10 minutes or so.
Okay, that sounds very good. That's very efficient and quick. That's great. We've had a question from Ali. Would FlowNMR work for high temperature real-time gas analysis? A great question.
Yeah, no, that's a very good question. So this is a bit more difficult, especially under the parameters which we utilize. Honestly, this is something that we can definitely discuss and implement. We haven't got any examples of that. As you can imagine, so having high pressure anyway is quite difficult to set up and maintain in your flow system. So that's something that we can do. With regards to the specific questions, that's something which we haven't tried, but in theory, it's very difficult because you don't want to introduce, so with the gases, you get bubbles, and that can, of course, influence your data acquisition of what you'll end up getting. So in short, I'll have a think about that, and I'll probably reply back to Ali at a later point, if that's okay.
Brilliant. Yeah, no, thank you. I think, yeah, it's always good. I love these Q&A sections because often it gives us a lot to think about, and all these different minds coming in together. It's a great way to think about new ways of doing things. So we've got a question from Bruno. Thank you for the presentation. It's a very interesting system for studying kinetics. But they say they're curious about the detection limits in parts per million. Are you able to help? I don't know if I missed that somewhere already. You may have already answered this, but let's go over that.
So, well, I says I'm not going to do parts per million because I'm going to argue as to parts per million of what in what. We're chemists, we'll go for molar concentrations. So I could say our usual limits for standard 5 mil NMR tubes with standard concentrations in that, say for proton and fluorine. A standard 16 experiment, we'd be confident detecting and quantifying down to about 10 millimolar concentrations. We can detect lower and reliably quantify lower at the cost of longer acquisitions, obviously. We haven't mentioned it, but carbon, you're looking at a couple of 100 millimolar for detection limits, and pretty much all the other X nuclei are going to be somewhere in between. In flow, we're probably looking at slightly higher, so probably 20 to 30 millimolar, both because of the slightly narrower bore of the flow cell, but also because, as we saw with the stacked data, there is a degree of signal attenuation we'll always have to worry about as soon as we're actually working in flow. So we haven't necessarily done the exhaustive experiments on just how low you can take it. But yeah, I'd say sort of probably 20, 30 millimolar proton NMR and fluorine should be fine in flow.
Okay, well, I hope that's answered the question. But again, do contact the team if you need any further clarification. I'm sure they're going to be able to help. So let's look at this question. How do you actually acquire spectra for reaction monitoring on your system? That's a good question.
That's another good question, and that is also a question we conveniently happen to have a couple of slides for.
Brilliant.
So we use our own software for data acquisition, which is known as called SpinFlow. And just to give an idea of just how easy acquiring data in flow might be, in this case, we're looking at what we can then do in our software is basically queue up one or more experiments. Let me just see if I can get the laser pointer to work here. Yes. Queue up one or more experiments. So in this case, I've actually got a proton NMR and a boron NMR spectrum queued up. I will admit, not exactly with, well, even then, the whole thing taking just over 10 minutes. But then actually basically saying, right, I just want to repeat that experiment, in this case, 100 times. And I want to restart my repeats every 15 minutes. This allows us to actually come in and, in this case, say, run that entire queue for 24 hours, no problem, if that's what we want to. We've actually got another slightly more sophisticated option. Now, this is actually configured more for our auto sampler mode, so not necessarily in flow, but if we actually wanted to do reaction monitoring on multiple samples, rather than necessarily queuing up a single set of experiments, we can actually build auto sampler queues with delays and loops within them. So in this case, we've actually got a queue built up, which is going to be looped through 42 times, during which time it's going to run a proton NMR spectrum, a boron NMR spectrum, and then have a delay of 5 minutes and then repeat. And of course, if we wanted to be very, very clever, we could then do this on maybe half a dozen positions on the auto sampler and do some in situ reaction monitoring of multiple in situ reactions in NMR tubes all at the same time.
That's really good. Thank you. That's useful to see some of that software as well. So thank you for sharing that. That's been really useful for, I'm sure, lots of people watching. Right, I think we've got time for maybe one more question. I think it's a good one from Desiree. I'm sure you're going to let me know if this is a useful question. I think it sounds good. Is there a separate probe for the flow cell?
Short answer, nope, exactly the same. The probe for the flow cell is exactly the same as the standard probe, is exactly the same as the variable temperature probe. And yes, and if I just give a sec, I'll go find the slide that's got the picture of it on.
Ah, brilliant, that would be useful.
Yeah. So if we're looking at here, so this is
so I don't think we, oh, there we go, it's showing now.
Okay, just coming through. So if we look at the bottom right, this is our probe once it's removed from the instrument, and we can see, yes, it's currently got its flow cell inserted. In order to switch it to using standard 5mm NMR tubes, we would literally just remove the flow cell, put a stopper in the bottom down here to make sure your 5mm tube doesn't drop out the bottom of the instrument, reinsert it back into the magnet, give it maybe 15 to 20 minutes to all re-establish thermal equilibrium, possibly reshim it, but we don't even necessarily have to reshim it after if we remove and reinsert a probe fairly quickly, and then we're good to go.
That's really great, and thank you for showing those images. That's it's always good to illustrate what we're explaining, isn't it? So that's really great. So I'm just going to remind everyone watching, if you do have a question, I've not got any time now to get through any more in the live webinar, but if you do send them into the questions box, they will be sent on to Robin and Assad, and they're going to try and get back to you within the next week or two. So do send them in, otherwise just contact them directly. But you know, if you've got questions, please do keep asking them for now. But I'm just going to say a big thank you to our wonderful guests today for joining us from Oxford Instruments. That's been really, really handy to see all of that really amazing information. So thank you for that. Now, if you missed anything watching, then you can wait for that recording to come through, and you'll have all that information nicely contained again in a recording, so you can catch up. So thank you for all of you watching. It's been great. We've had lots of engagement on the questions, lots of really detailed questions, which shows that you've taken a lot away from this presentation, which is always nice to see. If you've enjoyed this webinar, then please do check out chemistryworld.com/webinars for our future events. And while you're there, then do feel free to register for a Chemistry World account, where you can even sign up to our very popular reaction newsletter that includes a weekly digest of big stories from across the world of chemistry. But from everyone here at Chemistry World and Oxford Instruments, we look forward to seeing you again in a future Chemistry World webinar. Thank you.